Hi class, we are going to start with this chapter, Law of Universal Gravitation. Okay, so we know that Law of Gravitation is actually come from Newton. Okay, so this is the formula where F equal to G m1 m2 divided by r squared. So m1 will be the mass of one of the things, probably let's say this is Earth. Okay, so this is m1, the mass of the Earth. m2 will be the mass of, let's say this is Moon. Okay, so the distance between the center of Earth and center of Moon, we call it r. So the attraction force between Earth and Moon actually given by this formula. So how does this Newton got this formula? We have to come back to your Form 3 textbook. Okay, this thing look familiar? This is your Form 3 science textbook. Okay, so in ancient time, okay, people thought that Earth is the center of universe. Okay, so this Ptolemy, we call this geocentric. Geocentric means that Earth is the center of everything of universe. Okay, after some times comes Copernicus, Nicholas Copernicus. He said no, actually Sun is the center of universe. Okay, so from Copernicus, okay, we start from Ptolemy. Okay, after Ptolemy will be Copernicus. Copernicus said that Ptolemy said that Earth is the center of universe, which is very self-centered. Copernicus said no, Sun is the center of universe, and all the planets actually move in circular orbit. Okay, which we know that these two actually is a mistake. Sun is not the universe of it's not the center of universe, but Sun is a center only for solar system. So this one wrong. And then we know that all the planet is not moving in circular orbit. It is actually in elliptical orbit. Right. So this is a reason now we know this. So after Copernicus, okay. Before we have this, you see, look at textbook. We have Kepler, right? Before Kepler, actually, we have another great scientist. We call it Tycho. Tycho actually hired by Germany king and study the movement of star, because that time they already have a telescope. Okay, so after Tycho passed away, he has a student. We call it Kepler. Yeah, here come we have 3 Kepler law. First Kepler law, second Kepler law, and third Kepler law. Okay, so Kepler actually is he studied his teachers had not, and then he come out with 3 Kepler law here. Okay, look at oh, okay. So first Kepler law said that all planets move in elliptical orbit, where the sun is one of the focus. Okay, and then well, we know that not all planets move around the sun, only for solar system now. Okay, Kepler's second law said that the radius vector drawn from the sun to planet swept an equal area in equal time interval. Okay, and then the third law is said that the square of orbit period of any planet is proportional to the cube of the radius or semi-major axis of elliptical orbit. So this is second law. First law is rather easier, right? First law, we said that it is all in orbit. Second law, we said that if the time for the planet or for the Earth to travel from here to here and from here to here is the same, the area A and A will be equal. Okay, a planet swept out equal area over equal time interval. Okay, now we come back to third law. Okay, so third law is that we need a bit of calculation. This one we leave it after unit 3.1. Okay, here we come back here. Okay, look at your note. Okay, keep our Form 3 textbook. Okay, now we come to this thing. So how does actually Kepler learn about this thing, and how does this thing come from Newton? So we have to know that this thing, the law of universal gravitation law, actually comes from Newton. So how does it work? Okay, so after Kepler, that time, after Kepler came out with his first, second, third law, that time people don't really understand the relationship between force and motion. Okay, so we go back to time before Newton. People don't really understand force and motion. Actually, Aristotle has Aristotle, okay, suggested that force will cause motion. I taught it in class, right? Okay, so it means that anything that moves, you have to apply force, then only it will move. Okay, Aristotle said that force will cause motion. After that, Galileo Galilei come here. Galileo Galilei said, no, Aristotle was wrong. Okay, force actually will not cause motion, but force will change. Force will change. Okay, change is the keyword here. Force will change motion, which is aligned with Newton's first law of motion, saying that if a ball is moving in uniform velocity, it will continue its motion unless you have external force to change the motion itself. Okay, so that time it is a huge change. Okay, so beside then Aristotle has two things, right? Galileo has two theory. Galileo said that force changes motion. Okay, and then another one thing is force will cause an object move in uniform circular motion. Okay, so let's say this is Earth. Okay, this is Earth, and then let's say I push a ball here. Okay, the ball will not moving to only this direction with constant velocity. The ball is supposed to move back in a circular motion. This is the idea from Galileo Galilei. Okay, so after a very long time, people have no proof that proving it is in circular motion. But Kepler said it is in elliptical motion, and many of the scientists, they found that it is indeed not in circular motion, but it is in elliptical motion. But who can prove it, and who can calculate and come up with a formula about this? Okay, so here come in Newton. Newton is very important in determining the elliptical motion. Okay, so Newton has a very famous theory. We call it centripetal force. Centripetal force, which is also in your notes. Okay, so you look at this one. Okay, this is the first part. Okay, so this is the third part of your note. Centripetal force is actually given by Newton. We know that Newton is very great mathematician as well. So let's say this is point A. So when an object is moving out with velocity, and then we try to draw a line go through center of the earth, and then we write this is as B, point B. This is the velocity, and this is point C, and this is point D. So in mathematics, we know that there's an equation, right? In mathematics, AB square, the distance between this and this, AB square equal to BC times BD. This is from mathematics. Okay, we all know that Newton is very good in mathematics, so of course he knows the rules in mathematics. And then from here you can see that AB actually directly proportional to V, right? So if AB square, it is actually directly proportional to V square. So how about BC? Okay, so you're supposed to move in linear motion. Why is it the ball will actually turn back? There must be something that pull the ball come in, right? So we know that BC will be affected by force. Okay, clear? Huh? Because the ball is supposed to go straight. Once it is going in, there must be something that pulling it in. So that something is what we call force. We don't know what force is that, because that time we don't know what is weight yet. Okay, and then BD. What is BD? Okay, if we consider the time very short, BD is almost equal to DC, because BD can be ignored, right? So we can say that it is actually directly proportional to R. Okay, am I right? Okay, we know that BD equal to DC plus BC. If BC can be ignored, okay, so BD will be equal to DC, which is equal to 2R, right? Which means it is affected by R. So we will say that, okay, velocity is actually directly proportional to this one. So here we have the centripetal force that from Newton. That is how Newton has his centrifugal force of theory. Okay, now we come back. Okay, so by using this centripetal force, we still cannot determine that the planet is moving in elliptical motion, right? We can still argue that it is actually moving in circular motion. Okay, so we have to start with the very famous 40 shilling, okay, 40 shilling bet. Okay, there is a history between the Hooks, Ryan, and Halley. Okay, so Halley actually no, they are having just like scientists gathering, and then they have a question. Okay, Halley asking, the orbit actually moving in circular motion or it is moving in elliptical motion? Hooke said, of course elliptical. Okay, how you know that? Hooke said, well, I have the formula and I calculated it. Then Halley said, wow, I want to know the formula, how you got it calculated. Hooke said, no, I'm not going to share with you. We know that actually Hooke is kind of boosted people, and then he is very pleased to find mistake on others. So he is actually arrogant and what to do? He said that he claimed that he actually get the formula, but he said that I'm not going to share. If I share it with you, people will thought that it is too easy. Okay, so I'm going to hide it. When people try to find the formula, they will start to appreciate me. So that is according to story lah. So we know that Hooke is actually enemy of who? Enemy of Newton, right? Okay, Hooke and Newton is actually not going well. Okay, now Halley thinks, who else that I can ask for this formula? Of course, Halley will go to great mathematician Newton. Okay, Newton is that time he was in Cambridge. Okay, Cambridge University teaching mathematics. Okay, and then Halley came over to Newton and then he asked Newton, do you know that what do you think about the orbit of planet? Newton said, of course, it is in elliptical motion. Okay, so this is sun, it is in elliptical motion. Halley said, how you know that? Newton said, I counted it and I got the formula. Okay, then Halley said, please share with me. Newton said, oh sorry, I threw it away, I don't know where I keep it now, but don't worry, I can solve it for you probably 1 or 2 weeks. Okay, indeed, after 2 weeks, Newton sent to Halley his calculation. This is the great calculation that we call it law of universal gravitation. And then from this thing, we start to understand that actually all the planets moving in all elliptical motion. Okay, so this is what we call 9 pages paper. This is Newton handbook, Newton handnote, which is the 9 pages most expensive paper in human history. And it came from famous 40 shilling bet between 3 scientists, Hooke, Ryan, and Halley. Okay, from there, Newton actually published his first very famous book. We call it Principia, that's supported by Halley. So the detailed history actually I taught in class already. Okay, so here we have the formula of law of universal gravitation. We know that it comes from very famous 40 shilling betting. And then we know that how the centripetal force came by Newton. This one by Newton, this one by Newton. Newton that time actually only 20 something years old. He is still a very young scientist. Okay, now we try to link what is the relationship between the acceleration of the gravitational force of Earth with the universal gravitational constant. So we know that F equal to mg. This one comes from Newton. We know that this is actually where it came quite late after this. And then this is a formula that we learned previously. So we try to equalize this thing. mg equal to gmm divided by r squared, right? So m and m we can actually cancel it out, and then we got gravitational force actually equal to gmr squared. So after this calculation, Newton become very famous because people found that it can actually, Newton law can actually it is applicable from apple to planet. No matter it is an apple or it is a planet, we still can use this formula and this formula. Okay, now we come to the last part of today's lesson. Okay, so Newton universal law, we got it checked. Centripetal force, we got it checked. And then the speed of the earth orbiting the sun. So how we got this? Okay, so I will explain this next lesson. Okay, any question, you please pause in Google Classroom, and then we will discuss about it. Make sure you understand the lesson since that everyone cannot go out.